So you're prepping for an NLP interview, or maybe cramming for a final exam, and you need to get the foundations right. Well, you're in the right place. Think of this as your essential starter pack, a crash course in the classic tools that literally built the entire field of natural language processing. It all starts with this one big question, right? How do computers really understand what we're saying? It seems so simple, but the answer is just fascinatingly complex. Today, we're going to pull back that curtain and break down how machines first learned to make sense of our language, using the statistical methods that were the bedrock for all the crazy AI we see today. We're going to tackle this like we're building with Legos, starting with the simplest blocks and working our way up. So, first up is your classic NLP toolkit, where we'll model language as a sequence. Then we'll get into decoding sentence structure. After that, we'll see how to identify key entities in a text, and we'll wrap it all up with the absolute core concepts you need to nail for your prep. Okay, let's dive right in. Our very first building block is maybe the most fundamental idea in all of statistical NLP. It's this idea of thinking about language not as, meaning, but as a probabilistic sequence. The whole game, surprisingly, is just about predicting the next word. This is where Ngram models come in. Their job is to put a probability score on any given sentence. And listen, this is not just some dusty old theory. You use this tech every single day. It's the magic behind your phone's autocomplete. It's how a voice assistant figures out you said recognized speech and not recognized speech. And it's how translation tools pick the most natural sounding sentence. Now think about it. To perfectly predict the next word, a model would need to remember every single word that came before it. That's just computationally impossible. So the pioneers of NLP came up with this really clever shortcut called the Markov assumption. It's basically like giving the model a very short-term memory. Instead of looking at the whole sentence, a bigram just looks at the one word before it. A trigram looks at the previous two. It's this brilliant little hack that makes the whole thing work in the real world. But that shortcut creates a huge new problem, the sparsity problem. And by the way, this is a concept you really want to understand for any technical interview. Imagine your model saw the cat sat 1,000 times, but it never, ever saw the phrase, the cat pounced. Well, according to its math, that perfectly normal phrase has a probability of 0. That is catastrophic because it means the model thinks a possible sentence is totally impossible. So, how do we get around that 0 probability problem? The solution is a family of techniques called smoothing. The core idea behind all of them is actually pretty clever. You basically steal a tiny little bit of probability from the word combinations you have seen, and you sprinkle it over all the ones you haven't seen yet. It's like saving a bit of your budget for emergencies, just to make sure no valid sentence ever gets a probability of 0. Okay, so engrams are great for predicting the sequence of words, but what about understanding their grammatical role? That's our next building block, and it brings us to hidden Markov models, or HMMs. I love this part, because it's kind of like a detective story. The words themselves, the cat sat quietly, that's our evidence. We can see it. But the real mystery is the hidden state behind each word. Is it a determiner, a noun, a verb? An HMM is the tool we use to crack that case. And the algorithm our detective uses is called the Viterbi algorithm. It's this super efficient way to find the single most likely sequence of hidden tags for a sentence. It just moves forward, one word at a time, keeping track of the best possible path to get to each tag. Then, once it hits the end of the sentence, it just follows the breadcrumbs backward to reveal the winning sequence. This is the classic engine behind part-of-speech tagging. All right, so we've covered sequences, but we all know sentences aren't just flat strings of words, right? They've got this deep hierarchical structure. So our next step is to figure out how to decode that grammatical scaffolding to see how sentences are really put together. And that whole process is called syntactic parsing. The goal here is to take a flat sentence and build a tree out of it, a diagram that shows exactly how all the different pieces fit together based on a set of grammar rules. It's about moving past the simple sequence to uncover the hidden architecture of our language. And here's exactly what that looks like. It's not just the cat sat. No, it's a hierarchy. The words the cat team up to form a single unit, a noun phrase. The word sat is our verb phrase, and our grammar rules say that when you put a noun phrase and a verb phrase together, you get a complete sentence. By finding these building blocks, the machine starts to grasp the sentence's actual structure, not just its order. This is the heart of constituency parsing. Okay, so how do we build this tree efficiently? Well, a classic tool for the job is the CKY algorithm. Now, it's a dynamic programming approach, which is just a fancy way of saying it solves a huge problem by breaking it down and solving all the tiny subproblems first. It works from the bottom up, figuring out all the ways to combine words, then chunks of words, and so on until it has the full tree. For your prep, just remember the name, CKY, and know that it's powerful, but also pretty expensive to run. But grouping words into phrases isn't the only game in town. And this is a really crucial distinction to understand: constituency versus dependency parsing. Instead of building those phrase blocks, dependency parsing just creates direct links between words. It shows you relationships, like this word is the subject of that verb. Just think of them as different tools for different jobs. Constituency is great for languages like English with rigid structures, while dependency often works better for languages with freer word order. So, we've done sequences and we've done grammatical structure, but what about the actual real-world information that's packed inside the text? This brings us to our third big building block: finding the who, what, and where with named entity recognition. Named entity recognition, or NER for short, is a core information extraction task. Its entire job is to scan raw text and automatically pick out and label key things. The names of people, organizations, locations, dates, all that good stuff. Basically, it's what turns messy, unstructured text into clean, structured data you can actually use. So how does this work under the hood? A super common method is the IOB tagging scheme. It's best to think of it like a digital highlighter. B marks the beginning of an entity, I marks a word that's inside an entity, and O means the word is outside of any entity. So for Barack Obama, Barack gets tagged B per for the beginning of a person, and Obama gets tagged I per because it's inside that same entity. It's a simple system, but it's incredibly effective. And the tech for NER has evolved like crazy over the years. It started back in the 90s with systems based on handwritten rules. Then in the 2000s, we got models like HMMs. But the real classic leap was conditional random fields, or CRFs. Now, here's a great little nugget for an interview. CRFs were more powerful because they could look at the entire sentence at once to make a tagging decision, while HMMs were a bit more short-sighted. And of course, since about 2015, deep learning and massive transformer models have completely changed the game again. Okay, let's bring it all home with a final review. This is it: the high-impact summary of the core concepts you absolutely want to have locked in for any exam or technical chat about classic NLP. Let's put it all together. To predict the next word, we've got n-grams, built on that clever Markov assumption. To uncover a word's hidden grammatical role, we use HMMs for sequence tagging. To understand the full grammatical structure of a sentence, we use parsing. And to pull out the real-world people, places, and things from text, we use NER. These 4 pillars right here, this is the foundation that all of modern NLP was built on. And that brings us to our final question, something to think about. We've just walked through the absolute foundations of NLP, but in a world where AI is moving so incredibly fast, it's worth asking, which of these classic ideas are more than just historical footnotes? Which ones are truly timeless principles that will keep shaping the future of how machines understand us?